Hello, and welcome to the second review session for your final exams for Calculus 3208. The second section is on function operations again, but this time we'll be focusing on the product and the quotient of two functions, as opposed to the sum and or difference, which we saw in our last session. Alrighty, so let's get started. And we're going to look at certain aspects of what happens when we take the product or the quotient of two functions. First of all, we're going to be interested in seeing what happens when we sketch the graph of a function that is the product or quotient of two others. We're going to look at determining the domain and range of a product function, and then just the domain of a quotient function. And then we're going to look at writing the equation of a function that is the product of two functions, look at the product when we multiply, and then we're going to look at finding the equation for a quotient by dividing. Excuse me. Okay, so we move on. So our first example here, we start with two linear functions, f of x equals x plus 5, and g of x equals 4x minus 1, and we're going to create the product function h of x, which is f of x times g of x. And when we do that, we'll get simply h of x will be x plus 5 times 4x minus 1, and sparing you the algebra of a binomial expansion like you did in grade 10, we'll simply have 4x squared plus 19x minus 5. Okay, so that's how we look at that algebraically. Next we'll look at it numerically and see what happens there. So we've selected values of x at which we've already calculated values for f of x in this column from our first function, and for g of x in this column from our second function, and the values of h of x are simply created by multiplying the values of f and g together. So as an example, the first value of h of x that we have at x equals negative 6 is equal to negative 1 times negative 13, giving us positive 13 for h of x. And we can do something similar over here on our graph if we want to find a particular value for h of x. So f of x, first of all, is the red line that we have graphed, and g of x is the blue line, and h of x is this nice smooth curve that resembles a parabola, which should not be unexpected considering that h of x was a quadratic function. So let's look at an example again. We'll take right here, when x equals negative 2, we can see on the blue line that g of x has a value of negative 5, where each of these blocks represents, as we come down from the x-axis, 2 units, down to there to negative 5, and going up to f of x, we go from the x-axis again up a block and a half, so that's going to be 3 units. So we have a value for f of 3 and for g of negative 5, which should take us for our product function all the way down to negative 15, and if we look over here on the y-axis, that value is in fact at negative 50. So that's more or less in a quick rundown how we create the graph, the table of values, and the equation for a product function. Let's look now at some quotient functions. So for our example this time, we'll start by choosing the quadratic for f of x, x squared plus x minus 6, and for g of x, we'll use a linear x minus 2. So our quotient function will be h of x is equal to the difference f of x divided by g of x. Okay, so we can see that we just create the quotient, x squared plus x minus 6 divided by x minus 2. And we have our quotient function there, but it's usually a good idea to create, instead of just the expression as it looks in that sense, it's a good idea for us to factor it out and see if we can simplify. Incidentally, I just noticed that there is a typographical error on this page that I would like to point out to you. Up here it says, similarly subtracting the y values. That should, of course, not say subtracting. It should say dividing the y values. So I'll read that out for you, and with the correction in mind there. So up here it should say dividing. So dividing the y values of two functions at corresponding values of x produces a new function, right? So getting back to where we were now. Looking at our equation here, we take our numerator, which was a quadratic, and we're going to write it in factored form. So that becomes x plus 3 times x minus 2, and we can see real quickly then something jumps right off the page at us, since in the numerator and the denominator we have a factor of x minus 2 and a factor of x minus 2. We should realize that, algebraically speaking, we can remove both of those factors from our equation by cancellation, because they divide into each other to create 1, and all we have is x plus 3 left over. So h of x is more or less just going to be a linear function. We do, however, have to take note of the fact that we have this x is not equal to 2 business going on down here. So what that means is that while this is a graph, if we think about it in a graph of a linear function, we're not allowed to have x equal to 2, because then our original version of the function that we had written right up here, up at the very top here, would be undefined. And if that's undefined, then we can't have the value for our function at all. Okay, so let's see what happens with this when we take a look at it numerically. So numerically speaking now, once again, we can create a table of values for particular values of x to give us f of x here and g of x here, simply by filling in the values of x to our two equations. And then to get the corresponding values for h of x, I simply divide the values of f and g from over here. So let's quickly look at an example. H of x is going to be equal to 2 here. Why? Well, because at x equals -1, we had f was -6 and g was -3. So the quotient of those, -6 divided by -3, is +2. And the one thing that we should be careful of down there, and we'll take note of it again, is one more time, when x is equal to 2 over here, we notice that g of x and f of x both have a value of 0. But the more important one of those is the fact that it was g of x that had the value of 0, because that was the denominator of our expression. And when our denominator has a value of 0, what that means is we can't divide, so there's no value whatsoever. So let's take a look at the domain of this function. We're going to only look at the domain when we look at quotient functions for now. Later on in this course, we'll talk in great depth about curve sketching for rational functions. And when we do that, we'll talk about different ways to find the highs and lows and peaks and valleys and all kinds of neat stuff with those. And we kind of need that calculus business to help us figure out the range. So for right now, we can just say that to get the range, all we would do is to look at the graph. So we're going to make a note that to get the range, everything we would need about the range, we would just get it from the graph. So all we're going to focus on here, since we're not really looking at this part graphically anyway, is all we're going to look at is what is the domain of h of x based on f and g. All right, so starting off then, for this domain business, f of x right here, excuse me, was quadratic, so its domain is going to be all possible values of x. And for g of x, we had a linear, and so its domain is also all possible values of x. And that only stands to reason because we should know that polynomial functions are defined everywhere on the real line. For h of x, however, we notice that we've got something funky going on in here. There's some weird stuff somewhere around x equals 2. And it's important for us to understand why that is. Well, we already we knew that our graph had a non-permissible, or a function I should say, had a non-permissible value back at x equals 2. And it's exactly because of that that I'm not allowed to include the value at x equals 2 right here in our domain. Now, what that does to the graph of the function, we'll see that in our rational functions unit, which is coming up in a future session, or you've probably seen it already in your course. But what it does is it just sort of pokes a little hole in the graph. So what that means is the graph of h is defined everywhere except at x equals 2. So the domain has to exclude that. So using interval notation here, we just use round brackets at the 2 and create a union with another set that has round brackets at 2. And so therefore, we skip over that. We have disjoint sets, and we don't include the 2 as part of the domain. Okay, so that's in a nutshell how we create the quotient of two functions, algebraically, numerically, and it also takes a look at the domain. And we'll look at the graphical business with that stuff in much greater detail later on in the course. Okay, so next we're going to look at our first example. It says consider the functions given by f of x and g of x, and we're asked to do some things here. First of all, we have to algebraically determine an equation for f times g. So the first thing to note here is that when I write this notation, fg, with a little dot inside right there. Make sure you don't use an open circle because that means something entirely different. But if I just put a dot there, just like we use for multiplication, so what that means is the same as if I write f of x times g of x, writing them right next to each other, or what we call juxtaposition. So writing them right next to each other like this, and using this dot notation over here, those are really the same thing. So both of those are just different ways of indicating that we're taking the product of the two functions. So we'll start by finding our equation for h of x. And the equation for h of x, we're going to take x squared minus 2x plus 1, and we're going to multiply by 5x minus 3. And we'll do a little bit of algebra here. So first x squared multiplied by both terms in the second set of brackets gives us 5x cubed minus 3x squared. And then negative 2x multiplied through gives us negative 10x squared and plus 6x. And then multiplying by 1, we're going to have plus 5x and minus 3. So collecting like terms now, that gives us 5x cubed minus 13x squared plus 11x, and then subtract 3. And so we get this cubic function, h of x, that is the product of the two that we started with. So since what we ended up with here was a cubic function, finding domain and range is not going to be difficult. Cubics are polynomials too. Cubics are people too. Ha ha ha, just kidding. So what that means is that its domain is going to start at negative infinity and go all the way to positive infinity. And if you remember from another part of your 3200 course that you did, you're probably doing at the same time, most of you, what that does is if we remember the graph of a cubic function, typically looks like one of these two things. And either way, what we see is that we open up in opposite directions on a cubic function. And doing that means we actually touch every possible value of y as well. So the range of this function is also pretty straightforward and easy to come up with. So it's also negative infinity to positive infinity. If we were going to use our other notation for those, using set notation, we could just say the set of x such that x belongs to the set of reals. Or we could say the set of all values of y such that y is a real number as well. So that's another way to say those things and to be accurate. So we can use either interval notation or set notation there. Alrighty, so let's jump along to our next example. And this one, we're going to look at quotient functions instead. And first of all, on this one, I want you to notice over here the notation. When we write f over g of x like this, what we mean is exactly f of x divided by g of x. It's just a mathematician's shorthand. Instead of writing the whole thing out like that, really all it saves is maybe a couple of brackets, but we have two notations for it anyway. So first of all, it says not just to determine an equation, but a simplified equation. And that's important because when we go to do this, we can see that h of x is x squared plus 3x plus 2 divided by 2x squared plus 3x minus 2. And remember, when we're dealing with these rational expressions, it's a good idea to write them in factored form to see if we can simplify. So this one gives us x plus 2 times x plus 1 divided by, and our denominator is going to be a 2x. I'm sparing you the details of factoring because I'm hoping that just for factoring quadratics, that most of you at this stage are fairly well along in that, and you've done tons of that since grade 10, and then again in 2200 math and in 3200. So we'll spare the details of that for now, and we'll say that if we want to make all this work, we're going to have two factors of negative 2 on the end. So we'll go with a positive 2 here and a negative 1 there, and that makes plus 4 and minus 1 to make positive 3 in the middle. So there we are in fully factored form. And once we've gotten that far, we should notice that, looking carefully, we have an x plus 2 here and an x plus 2 there, which means our equation can be simplified to give us x plus 1 divided by 2x minus 1. We do have to be fairly careful here, though, because even though we did cancel out or divide out these factors, where they give us a value of 1 for each of them, because anything divided by itself, of course, is 1. That is still going to be a non-permissible value for this function. And we're also going to have a non-permissible value for this function when 2x minus 1 is equal to 0 as well. So if we're going to state those non-permissible values, I'm using my own fancy shorthand, NPVs for that. So if I'm looking at non-permissible values, if x equals -2, we would be in trouble. Or from this factor over here, if x is equal to +1/2, we'd also be in trouble because we'd have to try to divide by 0. And I'm not sure that we're capable of that. In fact, I'm sure that we aren't. Okay, so what we've done is we've simplified our equation and we've stated our non-permissible values. So knowing the non-permissible values very quickly allows us to write the domain. So the domain of this function, since it's the quotient of two polynomials, which are two quadratics in this case, can cover everywhere that those two quadratics are defined, which we already know is everywhere, except for the places where the division that we're trying to accomplish here cannot be computed, and that's where the denominator is 0, or in other words, at our non-permissible values. So we're going to have to break up our intervals twice here. First time at -2, so we're going to jump across -2 and give us a union to start at -2 again and go all the way up to +1/2. And then at 1/2, we're going to have to skip over that point, and then we're allowed to continue all the way on to infinity. So using interval notation, that one looks a little bit complicated. Of course, you could also write that using your set notation. But for now, interval notation should be enough. And we're supposed to be familiar with both of those equations anyway. So there you have your domain. All right, so those are both of our examples. Let's look at some sample questions that you might see on a test or an exam that have to do with those kinds of things. So first of all, we're given f of x and g of x in this question, and we're asked to find the domain of f divided by g. So let's think about what f divided by g would look like. So f divided by g is going to be 3x minus 1 divided by 3x squared plus 5x minus 2, which we can factor. So we have 3x minus 1 over, and now I want the factors of 3x squared plus 5x minus 2. So I know I have to start with 3x and x, and I have to have two factors that give me a minus 2 on the end. So let's go with plus 2 and minus 1. And we see that we get the same factor twice. Now, that is kind of irrelevant in this question. In this question, we're really wanting to know the domain of the quotient function. And whether these two factors cancel or not, we're still not allowed to have a value of x is equal to 1/3. So that's a non-permissible value anyway. And I think that's kind of put in there. It's this question to see if you knew that. And then the other non-permissible value, of course, will be at -2. So we have to restrict both of those and not allow ourselves to be fooled, meaning that D is the only possible answer here. So it's the set of all values of x except for -2 and 1/3, as long as x is a real number. And with that, we'll go to our next example. It says we have to write an expression for f times g, given that f of x is a linear, g of x is a quadratic, and we also have to state its domain. So very similar to what we did in one of our earlier examples. So in this case, f of x times g of x is going to give us 5x minus 3 multiplied by 2x squared plus 3x plus 9. So we'll expand all that out. First of all, 5x times everything will give us 10x cubed plus 15x squared and 45x. And then we'll multiply it all by -3. So multiplying it all by -3, I'm going to write it one space over and just below here. I sometimes do that to make it a little bit easier on myself to see where I can collect my like terms. And then we're also going to have a minus 9x there and a minus 27. So putting all that together gives us 10x cubed, and subtracting there will give us plus 9x squared. And then 45 subtract 9 will give us plus 36x and minus 27. So there's our function f of x times g of x. It's cubic. And we have to state its domain. So since this is a cubic and there were no restrictions placed on the original linear or the original quadratic we started with, the domain is going to be fairly straightforward again. Because cubics are polynomials too, which gives us x starts at -infinity and goes all the way to +infinity. So there's the domain of our function. Okay. So we'll jump along here, and this is the your turn question. So there's a chance for you to work out some stuff very similar to what we did throughout this recording. And I'll let you do that, so you can pause the video and go through it on your own. And then the next slide that shows up in here, which I'll show you in just a second, gives you a full solution for that. So that full solution you can look at if you want to pause now, work it out, and then check the solution. Okay, so here's the solution all worked out for the your turn question, which you can work through and check your own work to make sure that you had it correct. And then we'll just move along now, and we'll take a look at the key ideas from this section. So the key ideas from this section are, we have, first of all, when we write f times g using that notation, we're talking about the product of two functions. Just a reminder, when we write f over g, we're talking about the quotient of those two functions. But make sure we have to look for non-permissible values. So g of x is not allowed to be equal to 0. And the domain of a product or quotient function is the domain that we say is common to both f and g. And usually we're dealing with polynomials with no restrictions on them, so that's not a big deal. And for a quotient function, though, we have to be specific and say that the domain is restricted by excluding the values right here, where g of x is equal to 0, as we did. And the range of a combined function can be determined using its graph. And we can determine it directly from the equation later on in the course, but it requires a little more calculus than you would have done to this point. So thank you very much. Hope that was helpful. And if it was, then I hope to see you in the next session.